got it.
Can we just do a little review and then just lab?
Okay, here we go. Take a look. Now, all I want to do here on the last assignment before the test, the part 2 of the spheres assignment, there were a couple questions people didn't really understand, and some of these show up on the test. So I want to just quickly go through these. Now, one of them is this guy right here. Complete the table to specify the appropriate units for each quantity. All I want to point out here is the relationship between the units that we use to describe measurements made for radius, circumference, surface area, and volume. How those units would correspond to these different types of quantities that we would measure. Anytime we measure what we call a linear measurement, something we could measure with a tape measure, or with like a string that we could wrap around things and then find its length, stuff like that. Those we would measure in linear units. They'd be feet or inches or miles or meters or something like that, right? When we have to measure an area, right, something that is either flat or that we could cut up and lay flat on the ground, those kinds of measurements would have to be in square units, area units. Anytime we're measuring a volume, something that is truly three-dimensional, something that if we were to, let's say we had a structure that was made of ice, if we were to melt the ice and pour it into a container, it would have some real volume there, right? So anything that's three-dimensional like that, we'd have to measure in volume units, which are cubic units, right? So then, it's a very simple question. All that they're saying is, if our base unit is centimeters, so that we're measuring area in square centimeters, then what would be the measurement that we would use to describe, the units we'd use to describe a volume measurement? Yeah, centimeters cubed. We'd have to use a cubic unit, right? Make sense? Okay. Now, there's a little trick that we'll look at here in just a second that goes with this that makes this really simple. What about radius? A linear measurement, an area measurement, or a volume? Linear, sure. So that would be centimeters. You bet. What about circumference? Yeah, question. Yeah.
Is the circumference the same as the perimeter?
Yeah, the circumference. When we talk about perimeters of shapes, that means the distance around. For a circle or a sphere, we instead of calling it perimeter, we call it circumference. Okay. Yeah. So what would that one be then? Centimeters. Yeah, because that also is a linear unit. Imagine if we had a big circle painted on the football field. We could go out to the track shed and borrow their little wheel doohickey and wheel that around and see how far it was, right? That'd give us back a linear measurement, tell us the number of meters it was, right? Now, if you think about circles and spheres, if we look at the formulas for these things, the power of r always tells you what exponent goes with the units, right? So the formula for radius, well, that's just plain old r. The formula for circumference is 2 pi r. Surface area is 4 pi r squared. Volume is 4/3 pi r cubed. Well, notice that if there's just a plain old r, what's the power? 1. Good. So then notice that the power of 2 goes with the power of 2. The power of 3 goes with the power of 3. The power of 1 goes with the power of 1, right? See how that works? Okay? So there's one of them I just wanted to run through. Real quick, another one is this stuff. People were not entirely sure what to do with these. So say we had one like this. Say we had the surface area of a sphere is 144 pi. Find the circumference. Let's do this one. This is the hardest one we could get. This one, straight out. The surface area of a sphere is 36 pi. find the volume of the sphere. Now, if those formulas I just wrote up here, what do they all have in common? They all included, if we're talking about circumference or surface area or volume, what do they all have in common? Radius. Yeah, they all have an R in them, right? So then what we need to do here is we need to find the radius first and then plug it into the volume equation to get our answer. Now, where are we going to get the radius? Well, they give us the radius indirectly. If they tell us the surface area of the sphere is 36 pi, what was our formula for surface area? Remember? Of a sphere. Yeah. I don't think. Okay, so what was it again now for the surface area of a sphere? Not 2 pi r squared. 4 pi r squared. There we go. So surface area 4 pi r squared, and we're told that that's equal to 36 pi. So we got to solve for r there. What are the steps we could go through to solve for r there? Okay. So there's a couple ways. That's a good idea. Now there's a lot of different things being mentioned here. We could take a pi out of both sides, which is the same thing as dividing both sides by pi, right? Why not divide both sides? If we're trying to isolate the r, why not divide both sides by 4 pi? Right? If I do that, if I divide both sides of the equation by 4 pi, the pi's cancel, the 4 cancels, and then I get r squared is what's left over, equals, well, the pi's go away. 36 over 4 is what? 9. Okay, so that gives us the equation r squared equals 9, right? So r would equal 3 if I square root. Good. So r equals 3. Now, all we got to do is plug that into the volume equation, right, to find the volume of the sphere. Well, we can do that. We know that volume equals 4/3 pi r cubed, so then it must equal 4/3 times pi times 3 cubed. Good. What's 3 cubed? 27. So it's equal to 4/3 times pi times 27 over 1. Now we could multiply straight across here, but could we do any cancellation? 3 and 27. Good. 3 and 27 would cancel to 9 and 1. Okay, good. So now when we multiply straight across, we get volume equals 4 times 9, that's 36, right? 36 pi divided by 1 by 1. So we wouldn't even put that in there, right? So that's our answer, 36 pi. So Moodle, they want us to enter the pi symbol as a p. So our answer would just be 36p. Now that seems a little weird. Yes, ma'am?
How does that work if the surface area is 36 pi?
Ah, strange, isn't it? This one, it's a weird coincidence. But in this case, the surface area is 36 pi square whatever, say square centimeters. The volume just happens to be 36 pi cubic centimeters. It's usually that wouldn't happen. It's really a strange coincidence that we got the one case where the two numbers are the same. The units would be different though. Okay. All right. Now that's a weird answer in a way. You might be asking yourselves, why are we making it so hard? Why don't we just put pi in our calculator and make it a decimal, right? Okay. Can somebody answer that for me? Because pi goes forever. Exactly. Pi goes forever, right? And so if we want to get an exact answer, the only way to do that is to leave the pi in our answer instead of turning it into a decimal. The moment we turn it into a decimal, it's no longer perfect. It's just an approximation. But that is an absolutely perfect, 100% accurate answer because pi stands for pi. That symbol represents the number pi, which we can't represent as a decimal because it goes forever. Does that make sense? Okay, so there's a real reason that we're doing this. All right. All right, moving on. So that took care of those. Now the last, I wanted to take a quick look at stuff like this. People had some questions about things like this. This one is a little strange. Yeah. If we're trying to find out, can you picture what this shape is supposed to be here? We've got a normal cylinder, and then we've scooped out the top to make this hemispherical divot. Right? It's like a bowl that's half of a sphere. Okay? Does that make sense? You have to kind of picture it in your mind a little bit. So it used to be flat, but we've carved it out so it's like a bird bath now or something, right? It's got this perfectly hemispherical carved out bowl that would hold water when it rains, right? Okay?
Yes, sir.
So finding the volume of this thing would be no big deal. If we wanted to find the volume of this shape, what would we do?
The volume of the whole figure is the
Half sphere.
sphere.
Yeah, perfect. Okay, if we want to find the volume of this shape, we would just take the volume of a cylinder and subtract away the volume of a hemisphere, half a sphere, right? That'd be easy. Surface areas are a little tougher. The natural tendency for people is to want to subtract something away like that. They're thinking in terms of volume because that's more concrete. The surface areas, though, are a little trickier. Now, let's take the formula. Let's start with the formula for a cylinder, and let's just tweak it a little bit to make it fit this shape, right? So we've got the volume, or excuse me, the surface area of a cylinder equals 2 pi r squared, right, plus 2 pi r h. Now, dissect that for me. What do those parts mean? Biggie, put that away, please. What do those parts mean in that formula? What's the red part mean? The lateral area. So that's the tube part of this can, right? What's the pi r squared part? Oh, okay, those are the lids, aren't they? Those are the flat circular lids of the can. Notice there are 2 of them, one on the top and one on the bottom, but we don't have 2 of them here. We've only got 1 of them. We just have the one on the bottom, right? Here's on the bottom we've got this, we've got that flat lid. That's it. So our weird surface formula is going to have to be a little different. Some parts of this stay the same. We've still got a pi r squared on the bottom. Whoops. And we've still got a 2 pi RH for the sides of the can. But what's going to be a little different is going to be the top. Right? The top is going to be, the top surface is this concave hemisphere, right? And so I'm going to leave it up to you to figure out, what goes there, right? But that's how we got to do this. We've got to take the 2 parts that remain the same in the cylinder, keep those, but add that other weird third part instead of a second circle, okay? There's the challenge. All right, what else? Let's see.
Is that one of the harder ones you make?
It's honestly not that terrible. In terms of the math itself, the math isn't very hard. Conceptually, it's kind of hard. But the answer, once you get it, once the light goes on, it won't be that big a deal. The volume one we already said that's pretty simple. Just subtract. And then same kind of stuff for this. Finding the volume of that shape would be a piece of cake. It's just the volume of a cone plus a hemisphere, right? Surface area, we've got to be a little more careful with it. And then the last one let's take a quick look at is something like that. I think this is a really good problem. I like this one. Now on this one, they're asking you to find, you've got this cylindrical tennis ball canister, and they want you to find the volume of the air in the canister when it's filled up with tennis balls. So all the extra space not occupied by the tennis balls. So what's our strategy for this? I'm going to leave it up to you guys to actually do the problem. But how could we approach this?
They're just trying for some
Okay. Now, the assumptions we're making, and it says this, if you read the problem, it says this stuff. We're assuming that the tennis balls fit tightly inside this canister. So they're going to They're going to touch the edges of the canister when you put them in there. And the bottom one is going to touch the bottom. The top one touches the lid, right? So then the diameter of the tennis ball is the same as the diameter of the canister, right? And that distance must be the same as the height of the canister, right? How would I find the air? What's the trick here? Okay, but not area. You mean volume. There you go, volume. Right, we could calculate the volume of the cylinder and then just subtract away the volume occupied by the 3 tennis balls to find the volume of air that's still in there, right? Okay, good. Oh, maybe one more quick hint for you. There's another one that seemed to be a little problematic. Now, on this one, the Planet X one, the only hint I'm going to give you here is it's something you already know. But take this hypothetical situation. Say we've got a tree that is 112 feet tall. We have another tree that's 17 feet tall. If I asked you the question, how many times taller is the tall tree than the short tree? How would you answer that for me? The tall one's 112, the short one is 17. Yeah, you would divide 112 by 17, right? And you'd get an answer of, 5 point something, right? So he'd say, yeah, it's 5 point blah, blah, blah times as tall, right? Make sense? Actually, you probably get 6 point something. Okay? Make sense? Same kind of deal here, only this time instead of dealing with heights of trees, we're dealing with surface areas of planets. Okay? All right, I think we're set. Let's go to 205.